Okay, so I'm happy to be here with you this morning, and we can start directly. So before I go into the topic, I'll just introduce briefly the university, Gustave Eiffel. So Gustave Eiffel University was created 3 years ago, and it is the largest university in Europe dedicated to the city. So we have 3 challenges, which is like resource efficient, safe and resilient, smart and connected city. And something that is quite unique is that we are spread all over France in 7 different locations, and my lab is located here in Nantes. It's hidden here, I don't know, like it. We have 17,000 students, among them 200 PhDs, for about 2,300 staff, including researchers, and quite a good ratio between women and men within our university. My lab, that was introduced before, is called Geoloc. You have this logo that was created for us. And we are addressing positioning and navigation solutions. We consider those being a catalyst for the new forms of mobility. So what is illustrated here is, of course, shared mobility, but also crowdsourced information for improved mobility, better experience for travelers, and all what is related to using wearable sensors for improved mobility daily. And here you have some photos of my team. We have seen during those 2 days that there exists quite some interactions between wearable devices and humans. Among those, I could cite the possibility to generate some electricity. So we heard a lot about body thermal energy that can be used to produce some electricity for small wearable devices. Some tests have been done with marathon people that were able to use it for LED, for example. But you could also use like footstep kinematic energy. And this concept has been going on for nearly now 8 or 7 years. So when we look at it, we see that wearables are already interacting with humans for electricity purposes. But most probably they can interact in a much larger scale. And this is what we're going to look at it today. So the first thing that is actually driving the development of wearable devices is what we're doing in our lab, which is indoor and infrastructure-free positioning and navigation. You have some illustration here. And among the new wearable devices that you can see, they are targeting human beings on different locations. So you have here an illustration of the type of application and sensors you may have for a specific person. So if we start from the head, we're going to have all what is related to infotainment, smart glasses for augmented reality, virtual reality. If we go to the hearing part, then we're going to have all what is related to, of course, sounds, but also like conductions using bones for blind persons that you will have here. We see also now some jewelries coming here on the ears to measure some health information. If we continue down, then we go to smart clothings and also all what is related to arms and smart watches. When we move to this upper body part, usually we target health applications, but also fitness and sport. And in fact, sport activity is one of the main drivers for all of the wearable devices that you have. And then if you go down on the lower part of the person, then you will end up again with smart applications, but the more lower you go, the more you're going to close to business application, where we are going to target first responders is one of the key markets for it. But most probably tomorrow, when insoles will be ready for that in your daily shoes, you might be also using those sensors in your shoes for improving your daily motion. If you look at the existing positioning solution for indoor navigation, we have 2 main categories, and this applies also outdoors, but mainly indoor. You have a first category that is related to radio beacon network. Basically, you deploy tons of beacons in the infrastructure, and you're gonna get the signals, learn about the signals, and locate yourself. The second category consists in learning from signal characteristics, not necessarily provided by additional beacons, but already existing, or autonomous, that you carry yourself. Let's look at these 2 categories. The first category, radio beacon network, consists of installing beacons in a specific environment and measuring signal propagation characteristic. Most of the time, you pass in front of a beacon, and when you pass in front, you're there. Most of you have heard about these technologies when we were talking about COVID and contact tracing. Because contact tracing is nothing more than measuring the distance between two persons that are carrying beacons, and this is exactly what is done when we go indoors for positioning. The signals we're using are ultra-wideband, Bluetooth low energy, RFID signals, ultrasound, light, blah, 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 blah. The more we go, the more signals we see that are used based on deployed beacon. The benefit of the solution is that you get an absolute location by definition. Why? Your beacons are positioned in the network, so the coordinates are known in the local map. I would deploy beacon here, I would put the coordinates corresponding to this map. So you get location directly in the indoor map. It's scalable. So for business activity, it's very nice. You sell your beacons, and on top of it, you make money. But you also make money because you need continuous calibration of it. The environment is not steady in terms of signal propagation, and consider like an emergency situation, this room would be full, which will happen in a few minutes, then we would all run out because of a fire. Definitively what would happen is that doors would close, crowd effect would change signal propagation, the solution would not be efficient anymore. And if we think about a fire happening, then most probably some of the infrastructure will be destroyed. So here we have a question that is also related to accuracy. Of course, the more beacon you deploy, the more accurate you're gonna be. The other approach consists in not using the infrastructure deployed beacons, but learning from the signals. And this technology has been populated by Wi-Fi-based positioning using fingerprinting. Fingerprinting method is quite easy. Imagine this room, and I basically draw a grid with geographical coordinates, and I take my smartphones or any Wi-Fi measurement or receiver, and I'm gonna go on each point of my grid, and I'm going to sense a pattern in terms of signal signature. And then these patterns will go into a database that is georeferenced. In the online operation, what's going to happen is that the person is moving inside, and time to time, these patterns in terms of signals going to the cloud. And what is coming back to me is my absolute location. So this technique has become very popular because it's using existing infrastructure that is already deployed, and it's using geometrical constraint, which is like the indoor maps, to improve the localization through Bayesian approach. But again, a problem is a static hypothesis that is behind it in terms of signal propagation. So again, you have to go for continuous updating databases, and you cannot establish it for emergency situation. So what do? You go for inertial navigation system, or basically you go for what I call beacon-free or autonomous solutions. There, for those who are familiar with inertial systems, what we do is that we apply usually Newton's law, and we're going to use the angular rate, so the rotation of the systems, to basically track our orientation in space all the time. And once we have the orientation in space of our sensor, we're going to transform the acceleration that is measured into the local frame, where we're going to integrate one time the information for velocity estimation and a second time for position estimation. So that's classic kinematic, and it's very useful, because you get your position continuously, you get your orientation continuously in space, you don't need to deploy any infrastructure, so you don't need to know about the map, you just need an initial position. Now the problem of this is that you, basically for humans, you rely on wearable sensors. And you know better than me that those sensors are basically corrupted by a lot of errors. So the problem is that you're going to propagate errors at the integration speed. So the integration speed will be like t squared for the acceleration and t cubic for the angular rates. The consequence is that if you go with this approach without compensating anything, you'll have an error that is larger than 10 kilometers already after 2 minutes of walk with handheld sensors. So it's not possible to do that. As a consequence, you're lost. So where do you go? Right? Left? What do you do? And if you target like improved mobility, for example, handicapped persons, you can't go for something like that. So you're gonna have to search for something else. You're gonna have to search for continuous calibration tricks, how to improve your sensor measurements. You're gonna fuse with other measurements, like magnetic field, for example, indoors, indoor maps, etc., etc. But you're also going to use the kinematic. So you're going to learn from the humans as someone who is moving. And that brings us today to some of our questions. So if we can't integrate the measurement, how do we do? What we do is that we apply the technique called pedestrian dead reckoning approach. In a pedestrian dead reckoning approach, you're going to compute the position of the persons at each step. So I have my position here, and I'm going to estimate my position here. The way I do it is that from my wearable sensors, I get inertial signals, and I can get other signals, of course. And what I'm going to do is that at first I'm going to detect steps. And I'm sure all of you know that this is one of the first applications that people have been using to find out if they are fit or not, because the smartphones tells you like you've been doing so many steps today, and be sure it's overestimated. The reason is they want you to adapt the technique. So if you feel like you've been very active today, your mood tonight is going to be good. So globally, it's overestimated. So that's the first steps. Once you have that, the next steps will consist in estimating your walking directions and your step lengths. Once you have the walking direction and the step lengths, from the past position, you can deduct the next position. So in fact, the walking direction and the step lengths give you this vector here. And this goes on and on and on and on and on. And this is nowadays what is embedded in Apple iOS and Android operating system too. This is what is inside, and it is actually the backbone of any positioning system for pedestrian navigation. Artificial intelligence, of course, has become very popular in the fields. And one of the work that we've been doing in the lab is trying to understand the limits of it and the classification. So there exist two competing approaches. One is driven by human gaits information, and the other one is driven by sampling frequency approaches. So what does it mean? Human gaits will first assess your gait when you walk. So it's going to search for steps. Once the steps are done, it's going to have like a window of inertial information or magnetic information or any kinds of other signal information, and it's going to process that window for deriving your position. The sampling frequency approach does not take care about the human. They have a sampling frequency that is fixed, the signal is coming in, and everything is going to be processed as soon as they come. Here, the beauty of it is that you're going to learn from the human. Here, the beauty of it is that you do not need to take care about it. But, of course, you're gonna have potential troubles if you have changes that are not considered, if you have change of way of handling the sensors, etc., etc. So both have pros and cons. For more information, each time you see something like this, there is a paper behind it. So when I've said that, some of the questions we end up with are, what is the best reliable location on the human body to track a person on a map? Is it here? You've seen I could fit here. Is it here? Is it in a hand? Is it on a foot? That's not an easy question. And of course, when we talk about human influence, we also have to consider the impact of this reliable location on the human body, on the signal processing approaches and methods you're going to develop. So does this affect any of the performances and the quality? What we've seen also, and I'll illustrate it, is that depending on the navigation aids you are using, you're also gonna get different signals. And if we continue with what we heard a lot, which is that using artificial intelligence to go ahead, then the question will be how to train it. We've heard about it a little bit through the talks that were given. One of the key problems is labeling and continuous learning. So globally, what should be the best strategy to do automatic labeling of the data or continuous learning? Shall we use like a physics system, or shall we interpret the signals? Let's look at navigation aids and the need for individual approach. So as you can see here, I have a white can, I have a smartwatch, I have a smartphones with like connected with some smart glasses, and I could have also some textile. So depending on this navigation aids, I might move differently. So here you have the same persons that is working, is a blind person, that is working one time with a dog and one time with a white can. It's exactly the same person working on the same path. And you can already see that we don't exactly get the same motions, like you can get a feeling that with the dog it goes a little bit faster as without the dog. So if we look at it in terms of signals, you have on the upper part signals with the dog, on the lower part signals with the white can. And you have the norm of the acceleration, and here you have the norm of the angular rates. And this applies here for both cases. The box that is used to measure those inertial sensors data is located in the pocket of the person. So for the two cases, it's located in the same place. And just from looking at it, you can already see that with the dog, we have, in fact, higher irregularity in the signals. So, whereas with the white can, it's quite stable. And we also see that the dog has learned along the path because it was a way in and way back on the same path. And on the way back, the dog knows the path already, so it goes faster. So you can already see that just the same person, different aids for navigation, and it influences the signal pattern. If we transfer that into step detection. So globally here, what you can see is the filtered acceleration. This is usually the first steps of any navigation process that is searching for step events. And you see in black here the detected steps. And here you see the performances in terms of true detected steps. And you can easily see that with the white can, it's much better than with the dog. And that is strongly related to what happened before, because I have different patterns, but I have the same signal processing that is applied for the same person with different navigation head. So here, as a consequence, the more chaotic or volatile dynamic that happens with the dog induce more high-frequency components, and since we are looking for low-frequency component for step detections, of course, it impacts the performances. And we are more happy with the white can in this case. So that asks a question like, how can we address that? How can we develop techniques that are going to be more immune to those changes? The way we do it in the lab is that we adopt some artificial intelligence techniques. Why is it needed? Another illustration is given here. So without giving the name of the equipment, you have here two scenarios. One is a straight line with a smartphone, a wristband, and our solution, which is artificial intelligence-based, called Smart Step. And here is a complex in and out scenario. Complex, I mean, the person was changing hands position, was climbing stairs, descending stairs, going indoor and outdoor. And what you can see is that on straight line, everybody is in the same category. So you've seen it with the white can before. When the signal is stable, it's working fine. But when you go for daily activity, I was telling you that podometers on smartphone are giving you a better image of yourself than you think. So you can see here, this is a classical podometer app on a smartphone. It's going to over-detect steps by 34%. For a wristband, which has been designed for that, then it's a little bit better. It's customized for the application. And our artificial intelligence technique overestimates still, but much smaller. Okay. So here we're learning from the initial signals, and basically we work on both simultaneously, the gyroscope information and the acceleration information. We switch between the different models with some techniques, and it is a histogram gradient boosting approach. And one of the key problems you have when you want to do something like this, it's learning. You need to label the data. And Now that we say that human navigation aids is impacting the learning, is impacting the signal pattern, it's going to impact the learning too. So the problem is, what shall we do for learning? So if we look at what would be what is the correlation between the upper and body part locomotion, so you have here a mocap system that consists of several sensors that are on the human persons. You can get a sense that upper and lower body are correlated. So what usually we tend to do, the first approach when we try to train data for artificial intelligence is to search for the true data, the reference data. And the reference data, when we talk about human motion and gait, usually it's the footsteps. So what researchers are classically doing, and they are going to use a mocap system, motion capture systems, they're going to get the true instant when they are walking with the mocap systems, and they will consider this instant as a true label for learning. So globally, here we have the signals that is collected by those boxes at different positions. So we have like the foot-mounted device, right upper leg, pelvis, and head. And this corresponds to the true step. So globally, it's not always the same just because when you go here with the steps, the other one is in the air. So if you plot each steps on the same foot, it ends up on the flat period and not the flat, and the flat and not the flat. But if you project it in the different other signals, because everything is synchronized, you get a feeling that something is strange. Because you don't necessarily get the same characteristic on the other signals. So I just said, why not using a reference system for labeling the data? That's strange. Does it make sense? Let's test it. Let's test like using the physics or the brain. So what I call the physics will be the true mocap systems, where I see my legs, and most probably my feet are telling me the truth. And the brain means like analyzing the signals, looking at the patterns in detail. So it requires like much more effort to label the data. So we use like 10 subjects, a big data set, two same devices that basically we develop in our lab. It's called IEEE hardware, where we have inertials and GNSS and magnetic. All the sensors are integrated by ourselves. And we use two techniques to label the data. One is the physics. So basically, it's a detector that we developed for foot-mounted navigation. We won some major competition in France, and the startup company that was mentioned is using some of these techniques for soldiers and firefighters. So it gives you this true instant of the flat foot when you walk, when you run, when you jump, when you sidestep, whenever you do something. And the brain is using the smart step technique that is using artificial intelligence. So basically, there we look at the signals and we search for pattern. And that, of course, costs more in terms of investment, human resources, and time. This was then tested with like three different scenarios. Two scenarios with people that have no issues with sightseeing, and one scenario with a person that is blind. And you also have like a more difficult scenario along the path. Some are going indoors, some are having different like handheld carrying kinds. So texting is like, I call it the birthday walk. It's basically when you carry a birthday with candles and you don't want those to blow out. So researchers love to go for that approaches because then you're like a robot like this. So whatever you do here, exactly what's happening on your feet. But naturally, like we don't walk like this. So if you have a wristband, you're gonna have like a swing motion. So this one is basically combining the birthday cake and the natural walking. So you have here three tests that has been done, where we basically use the physics and the brain to learn. So here you have the outcome of it, and if we just concentrate on this table, and you have details in this paper, what we can see that when you use the physics, we have some troubles in terms of true positive as compared to the brain. So the brain is working pretty well. I detect, even in the blind scenario, I detect like 96% of the steps. But with the physics, I only detect less than 4% of the steps. So that's good and bad. Good because I have something that can work, but bad because I was dreaming for automatic labeling for artificial intelligence, and this is not possible. So here, unfortunately, the human has a strong influence on the data that I'm sensing with my wearable devices. So I don't know if it's the good or the bad, but somehow we are keeping some control over intelligence. Let's look at a completely different impact. What would be the impact of a human body on satellite-based positioning? I'll make a quick recall or recap on how GNSS positioning, so global navigation satellites, system positioning is working. Within GNSS, we have like the GPS, we have the Galileo, we have the GLONASS, etc., etc. So the way how it works to get a position using GNSS signals is basically to compute the intersections of signals that are coming from space. So if I get signals coming from space, I can compute the distance that separates me from the signals, the satellites, sorry. If I know the position of the satellites, then I can compute the intersection that is here. Now, to compute those distances, what I'm going to use is the time to travel. So the satellite is going to send the signals, and the time it needs to travel to me will be multiplied by the speed of light, and I will get a distance. For being able to do that, there is one strong hypothesis, is that my clock and the clock of the satellites, they have to be synchronized, which is not the case. So the consequence is that we need 4 satellites for getting in position instead of 3, because we have 4 unknowns, 3D coordinates, and a synchronization failure. So I need at least 4 satellites to compute my position. And this is here. I even have one more that will give me some redundancy. Synchronization failure is the major problem, but it's not the sole problem. So we have plenty of additional effects that are going to slow down the signal propagation, going through the atmosphere, being on the zenith, having like reflections, and this is one of the major problems we have in cities. My receiver here in my smartphone has no clue that my signals came bounded like this instead of direct. And the consequence is that these signals will end up somewhere here if it's considered as a line of sight. And here it's going to be the same for the other one. So when we deal with GNSS in urban environments, we have to address what we call non-line of sight signals. Those that are not coming directly to us. And that is going to introduce a lot of errors in my positioning solutions. So, as a consequence, one of the key stuff that researchers are trying to do is to differentiate line of sight from non-line of sight signals. The other problems we have, and that is going to impact the solution also, is the geometry. We are looking for an intersection here. So if ever all my satellites would be located here in the zenith, the intersection would not be nice. If I have satellites in zenith and one satellite in the horizon, suddenly I will get a better intersection. So the geometry is also going to impact the accuracy. So what we'll look at for positioning is, with GNSS signals, is the differentiation between loss and loss, the geometry of the satellites, and of course, the more satellites I'm going to observe, the better it's going to be. That's the reason why nowadays you see in wearable devices like smartphones and smart bands, receivers that are compatible with multiple constellations. So nowadays it makes no sense to buy a receiver that would be GPS only. So you'll get solutions that are GPS, Galileo, and GLONASS, etc. Beidou even for the Chinese one. And the more signals you're going to get, the better it's going to be too. So the latest developments have also enabled to track signals on 2 different frequency bands on low-cost wearable devices. So now that I've said that, the question I want to address now is where shall I fix my GNSS antenna to get the best location, best positioning? So we saw in the introductions that you can position wearable device on the head, you can position wearable device here on the upper lower body part, and you could also position it on the shoe, which is becoming more and more trendy for business-to-business application and safety application. Head, people don't want that. Nowadays, people are not looking for wearing a hat that is specific with like a GNSS antenna on it. Maybe like smart glasses may bring it, but it's not possible to have like an antenna that is tracking GNSS signals on smart glasses. So what we're going to look at is two positions, the hand and the foot. So let's make a vote. I'm going to ask you, where do you think it is best to locate the antenna, the GNSS antenna, now that I'll describe how it works? Who is voting for the handheld? Raise your hand. Don't be shy. Okay. And who is voting for the foot? Let's see. So to address that, we're going to adapt the receiver's point of view with a camera that is located on the foot and one in the hand to analyze the visible satellites. The experimental setup consists in one person that basically has two units. So this one is a unit that we develop in the lab that has all the inertial signals, the magnetic sensors, barometers. So you have all the description here of the sensors that are in it. And we also have like a GNSS receivers at the 500 frequency, which is like a dual frequency receiver from u-blox. And we've attached rigidly on it a GoPro Max 360 camera that will be used to see what we see in the sky. All the data are highly synchronized at microseconds because we use the GNSS signals for synchronization. So all the wearable sensors here, although there is no wires between those, they are all speaking in the same time frame. The camera data have to be calibrated. So first we need to extract the information. Second, we need to calibrate the camera as classically. We need to go from hemispherical data to rectilinear images. So we need to shape the camera images. And then we're going to bring together data coming from the GNSS receivers. So GNSS receivers is in this box. So we need to bring together the two reference frames because we don't have the same reference frame for the camera and for the GNSS box. So a conversion is needed to align everything in the same reference frame. And the final step consists in projecting the visible satellites into the images. An intermediate step consists in extracting sky areas. So we've been testing different techniques. Classical signal processing techniques that are segmenting the images using like a grayscale, k-means, mean shift, edge detections. But we also tested some artificial intelligence-based technique using deep learning, neural networks. We're testing fully conventional networks, high-resolution networks, pyramid scene parsing networks. And we ended up like with a latest approach that was developed in 2022 that is providing the best performance we call the mask-to-former. Again, like you have a reference here. And it shows here what you get. So some of the problems we got here is that sometimes like clouds, as you can see here, are not detected as sky, but they are detected as buildings and obstructions, etc. So these are some of the classical problems we got. And here is what we get. So you have here the sky view from the camera, and on top of it you have visible satellites. So of course those two images are synchronized, so you get the same information from the foot and the hand. In green here you see the visible satellites line of sight. In orange, you have visible satellites, but with reflection. So those were the red one on my previous plot. And in red, it's satellites that are not visible on this receiver, but are visible on the other one, okay? So those are the different colors. We developed like a GUI interface where we can see like different information from the different acquisition. Let's see what we have. So here you have two samples of images that have been extracted, and to make it more easy to observe, I've added some lines between the visible satellites so you can more easily see the patterns. You also have on the top right the visible satellites for the hand and for the foot. So the hand is in blue, the foot is in red, and the dashed line is all the satellites, and the solid lines correspond to the line of sight satellites. And here you have the foot pass, or I would say pedestrian pass, because in red you have the handheld pass, and in blue you have the handheld pass, and in red you have the foot-mounted pass for the same persons in the city. So if we start from here, the first thing we can see here is that we have here a better foot track than handheld track. So this tends to go in the majority of your vote, which is that the foot-mounted is providing a better solution. By the way, it's counterintuitive, so you all voted counterintuitive. And here, I guess this one is dying from the battery. So here you can see that you have like more visible satellites on the foot. It's okay, Anil, don't worry, don't worry. I can go there and so on. So here you can see that you have more satellites visible on the foot than in the hands, which also goes toward what you were saying in terms of amount of satellites visible. Now, if we look at this, here you have some percentages. So if you can see between the hand and the foot, here and here, there is a difference, but that is not that big. So you have like between the 50 and 50%, 53 and 51 case, and here you have 69 and 72. So there is a difference, but this difference is not that big. The main difference is more going to come from the geometry. And this was surprising to us. At first, it was surprising to us that the foot-mounted unit would provide more visible satellites than the handheld, because nowadays everything is developed on handheld sensors. That's the first. And the second was to observe that, in fact, when you have it handheld, here what happens is that the body mask here is larger in the scene. And here is the zenith in terms of satellites. So globally, you're hiding more satellites. But more important than hiding, what's happening is that the geometry here, when you occupy the space, when it's on foot, it gives a better morphology. So if I look at this one, it's even visible here on this one. You can see that the morphology in terms of masking in the image is completely different. So if I summarize this, globally what we observe is that we have more satellites visible on the foot than in the hand. So you voted correctly. And again, I was surprised, because it's very counterintuitive. Even for us being like specialists in GNSS navigation. What we observe is that the upper body part obstructs more the sky view with handheld GNSS receiver, and we get more satellites, line-of-sight satellites on the foot. But more important is that the morphology of the masking area is larger for the upper body part than the lower body part. So globally, we get a poor accuracy because we have a poor geometry when we have handheld receivers as compared to foot-mounted antennas. It's okay, it's the end. And if you want to, again, like to get some more information, you always have like a reference to papers that you can pinpoint at. So to summarize this, what I try to show you today is that the human morphology, the gait, and the wearable sensors placement is changing the data that you are sensing. And it's not often that people are looking at that. If you analyze the impact of the human on the data quality, you will see that it raises quite a lot of questions regarding the development of individualist approach. Yesterday, one of the keynote speech was talking about getting customized solutions based on applications that are targeted. And here, I would say that we are also going to customize a solution based on who you are as a human being. And when I say that, of course, it's very interesting, but it raises many questions because it's like a non-ending question, so like an open loop. Where does it end? Where do I stop when I do my development? And one of the things we are hoping in the lab, and we're working on it, is that artificial intelligence is maybe a chance to bridge that. So globally, to mitigate personal and environmental variations. And this is something where usually you don't necessarily see artificial intelligence. You see it usually as learning unknown problems where you have true labels and true information. But here we see that it can definitively help you to adapt automatically to who you are daily. And I hope that now that I've presented it, you might be tempted to test your own wearable devices and see if it's providing you good information about yourself, or if you were able to destroy it in an easy way. I hope I gave you some clues. And this is where I conclude. I've added this picture here, as Anil was introducing it before. We just launched a new journal that is called Journal of Indoor and Seamless Positioning and Navigation. It's a full open access journal where actually I'm honored to be the founding and editor-in-chief for the first term. So you're welcome to submit your nice research over there. Thank you.